Dave if he wanted me to introduce him, but he said he's perfectly capable of introducing himself. So we're going to let Dave introduce himself. What was your last year service pin? Is that?
I don't know. Lost memory.
Yeah, that was a long time ago. Dave has been here a very long time, entire career, and we're very happy.
Okay, so actually I'm pretty easy to be introduced because I only have one career. I joined Geophysical Lab in 1968 and have been here ever since. Before that, it's probably not important and I don't remember anyway. So the reason I'm giving the talk today, and this is not a regular seminar time, is because this work will be published soon. It's in press, actually in press, and we haven't received a gallery proof yet, but they just said I need to let them know where I'm going so that the gallery proof can be responded immediately. It's in press in Nature, and I consider it's a very important work. So I like to talk to give a talk before I leave. I'm leaving next week, later this week, and I won't be back for 2 weeks. So 2 months. That's right. And so I like to give this talk.
I'm going to turn the lights.
Yeah.
How's that?
Will that be better? Okay, good. Okay. The talk is about the story. The story will be shocking. At least it's shocking to myself. It's a very unusual thing happening, and it turns all the conventional wisdom, what I used to believe, what I used to know, upside down. So later you see what this is about. Okay, the conventional wisdom about oxygen fugacity that we all took for granted, oxygen fugacity of the free oxygen, and several other things. And then what we have done experimentally, and we're finding, and now it's beyond any doubt. And then what the new paradigm of those conventional wisdoms will be, and what's the impact of this finding to many different fields, including geobiochemistry. Okay. The subject is very simple. If you pick one element to study, what would be that? It has to be oxygen, because oxygen is the most abundant element in terms of atomic percentage in Earth. And oxygen is also formed refractory minerals, or silicates, as well as volatile compounds. So oxygen is sort of like a huge balance of other elements you analyze. So we really do not know much about oxygen budget, oxygen reservoir, oxygen cycle. We don't talk about oxygen cycle. We talk about hydrogen cycle, carbon cycle, and so on. We don't talk about oxygen cycle because it's just everywhere. So it's hard to constrain that. So the way you constrain that, or the way to think about it, is how you think of some term called oxygen fugacity. That's also something everyone is just in the background of your education. Everyone should know about some oxygen fugacity. Okay. Oxygen fugacity itself is defined by iron oxide, solid phases usually, like iron wustite, magnetite, hematite, and so on. Sometimes you add some other thing like ferrite, some quartz there, but basically it's iron oxide. That's one way. When you experimentally define that, one way is to define that by some fixed point of the buffer. And another way to do it is using gas mixing. Then it's usually some volatile oxide gases like CO2, H2O, and H2O, H2, and those gas mixing defines oxygen fugacity continuously. Okay, so and if you think simply, for the Earth, what do you want to know? Oxygen, number one. The number two has to be iron, because that's also the most abundant element by mass in the Earth. Also, the interaction between oxygen and iron is defines everything, like how the Earth's the core separate and how Earth differentiate. So the third element may not be the most abundant element, but it's the most mobile element, and it can move things around, and it's related to other reactions. For instance, like how does oxygen react with iron in air? They do not just simply react. Usually you need some water, then it rusts. So hydrogen is very much related to this all those reactions. And also in the buffer experiment, if you want to control the oxygen pregacity, you put some hydrogen there, put some water there, because water can diffuse through the membrane and so balance the oxygen pregacity. It's a mobile carrier for everything. Okay, so at Geophysical Lab, you have to give when I came in, say 50 years ago, I was told you have to give a Turner diagram. So that's the sort of trademark, and I think this probably will be a better logo than that sphere, unused sphere. Okay. So I'm talking about is this Turner diagram. Actually, this is not well defined at high pressure, surprisingly. So this is the oxygen ion binary, and then you put hydrogen on top, and we know this there's a H2O, and there's a rust, and it has many different forms, alpha, beta, gamma to epsilon, and it's but the composition is FeOOH. Okay, so let's just look at binary. Start with binary, and this has been well studied, and the interaction between iron and oxygen are pivotal to everything of the Earth's formation of the core, differentiation of the mantle, and even oxygen in the atmosphere. And the UV phase certainly did many of those things. And recently also there are new stoichiometry found. But no one studied this side. It's strange that it just totally escaped everyone's imagination because of conventional wisdom. And they think that, okay, now, nothing is that oxidative. But this, on the other hand, this is where we live. We live in hematite oxygen surface. That's the atmosphere that we have. Okay. So the conventional wisdom number one is that the mantle is uniformly reducing. That is taken for granted. That on the surface you have oxygen, and then at the core is iron. That's so. I think the reason that this became conventional wisdom is, okay, now this is a very reducing iron. This is oxygen, so it has to be sort of gradational like this. Okay, so I'm trying to challenge this later. Okay, that's why I said I'm shocking. This is shocking. Okay, now for this series, everything defined, or oxygen pregacity is defined by the stoichiometry of those things. So those are like buffers. Okay, and now there's new stoichiometry found, but never over this side. Okay, now the conventional wisdom number two is people think H2 is reducing. It is reducing at ambient condition. So if you put H2 and FeO together, you reduce some FeO and form some water and reduce some to that side. So it is reducing. Okay. But so everything here looks like it works nicely with the stoichiometry, and those are all the different ratio of Fe2 plus 3 plus. Like this is you have 2 Fe3 plus and 1 2 Fe3 plus and 1 Fe2 plus, and this is all 2 plus. This is all 3 plus. I just ignore the non-stoichiometry part. Okay. But at high pressure, recently, Alex and the other theoretician like Organov found that stoichiometry is something. It's almost meaningless. It can be changed any way you want with increasing pressure. So they looked at something that the way the conventional wisdom has to be 1-to-1 sodium chloride, and then you learn that in your high school, even probably elementary school. But they form many different stoichiometry, like Alex found. Okay, sorry, this is any ratio, 3-to-1, 2-to-1, 3-to-2, 1-to-1, and so on. Many different ratio. So the way to read this, if you're not familiar with that, this is called a Hull, H-U-L-L figure. It's a plot energy versus stoichiometry. Anything far below a straight line is a stable phase. For instance, this is, if you look at sodium and chlorine, and then sodium chloride is below this line, that means it's more stable than sodium plus chlorine combined. Then at low pressure, indeed, that's the only stable phase. But increasing pressure, you start to see that those lines start to curve. That means if you draw a straight line between sodium chloride and chlorine, and you will see this phase below the line. So here, sodium chloride and sodium, then you like exaggerate the vertical scale, you see those below that. So the theoretical calculation means that anything below that is a stable phase. Okay. So this itself is kind of shocking chemistry, because that means that you don't look at the charge anymore. You just look at whatever the lowest energy phase will be stable. Okay. Now, so then we look at the FeO. Okay. FeO, initially I was interested more on this side, like between iron and FeO, because that's the iron boosted side. I said that the lower mantle are mostly iron boosted buffer. But instead, Dr. Yang Kim found that there's a phase that's sticking out, FeO2. It's way below everything else. And it really sticking out at like so some. So this was last year. And I said, well, this couldn't be right. Just keep calculating, and he just keep changing some parameter. Although those called ab initio calculation with no adjustable parameter, they have a way to adjust it anyway. But with all the adjustment, this FeO2 you cannot get rid of it. It's just very stable. And actually, this is not only, he's not only a person to calculate. Later, when I published a paper in China, I showed this to Yemin Ma. He said, yes, we have seen this for 5 years, but I just couldn't believe it. So so just tell his students, to keep changing the subject, and iron doesn't work. Okay. So but Dr. Yang is very insistent. He said, well, now you have to try that. Okay. So I said, okay, now I said, okay, now maybe it's energy stable, but for theoreticians they have another way to look at it. They look at whether the phonon stability, and that means something may be energy stable, but if phonon is stable, then it couldn't exist. But so this phonon calculation is also very stable. And this phase has FeO2 has a pyrite structure, and this is pyrite is very simple. It's a Pa-3 or bar 3 structure. So okay, so well, it didn't hurt to get someone to try it. So Xian Hu was he's a postdoc working on my geochemistry and geophysics grant. Say, well, why don't you just take some Fe2O3, put in oxygen, and compress it, and later heat it and see what happened. So he compressed it to 76 GPa. Before later heating, it's just a hematite, haploid phase of hematite. This is known, and also has X-ray diffraction of oxygen. So this is X-ray diffraction pattern. But once it heated, this formed some spot, and this is not hematite, not oxygen. It's a spotty pattern that's doesn't seem to fit anything known. And here we know the FeO2 is a possibility. So this pH3, and you can see those aside from the Fe2O3, some unreacted part, all the storm peaks are pH3. That's a cubic, so it's very simple to compare with. And if you compare with this, you have all the PA-3, the calculated despacing, the measured despacing, and they agree very, very well. And it has all the calculated peaks out there, and all the peaks are accountable. So this we refined this, and then found then this is found a very small difference, and with some residual Fe2O3 left there. The structure is the pyrite structure or PA3 structure. The sample became, after the heating, became partially sort of translucent. Before it was dark. The hematite was dark before, and then heated, became translucent. The diffraction is very spotty, which is good for us to really identify the structure, because if you have a powder pattern, even you have 10 lines agreed, it still can be fortuitously that some structure that you have the line agreed. But if it's a single crystal, each crystal has its orientation, then you can check the orientation matrix and check all the spot points. Then there's no doubt what it is. So this Li Zhang developed a new method. Before high pressure, there were two methods. One powder diffraction, one single crystal diffraction. I have sorry, thank you. It's not a cold, just allergy. It's the second one. So this is called a multigrain analysis method, and it's actually I think that would be a new way for everyone to do high pressure that way, because the powder pattern has a disadvantage. It's you're never 100% sure of the structure. The single crystal is hard to maintain at one single crystal, but usually you end up with hundreds of crystals. But this method you can analyze hundreds, even thousands crystals, as long as they form individual grain. Then you can identify with some software. You can identify each individual the orientation matrix, and then separate them, and to find out how many independent crystals they are. In this case, we found like several hundred crystals, and we picked 5 crystals, and you can see that you analyze the 5 crystals, they agree very well. Each one is individual crystal have a different spot. So there's no doubt this is FeO2 with pyrite structure, and you can see that this OO bond and then this FeO bond, and this OO bond means that this OO bond. This means that this one, you can, if it's like pyrite, the iron is actually 2+, but oxygen has 0. Some oxygen with this is like O2. You can think of it as O2 dissolving FeO. And when we release the pressure, get to 31 GPa at ambient temperature, the pattern disappears. So this is quenchable from at high pressure to room temperature, but not quenchable to ambient condition. When we're ready to publish, actually there's another paper came out on archive that another group from Cambridge and the University of London, Richard Lead and Chris Pickett group, they also got the same result as with FeO2 there. because it's just a theoretical calculation, and no one believes that, and they probably don't believe it themselves. So it's just published in some obscure journal at the end. But now we have an experiment, so we know this exists. But that doesn't mean that this will have much impact, because when we submit to science, they immediately return it. They know it's not sent out to review, because they say, okay, now this may be interesting to some crystal chemistry, but it's not important to Earth's interior. Everyone knows that Earth's interior is very reducing. I mean, where do you get oxygen? I mean, if you even you can make this at this pressure, you cannot find oxygen. Okay, so then we say, okay, maybe you can extract some oxygen out of the water. So if we start with FeO2O3 and put water there, if you can take the water out of here, then you can make this thing. But so at ambient condition, you work the other way around, because this is more stable than the 2N member. But at high pressure, maybe this will change. So we tried another experiment. At low pressure, then if you put water and iron together, it forms FeOOH at low pressure, and then this FeOOH is called goethite, and at high pressure it forms some epsilon phase. It's a distortion of the goethite phase. And then if you can carry, so basically science editors say, well, if you can show me that you can take a piece of a valid assemblage on the surface and put it in depths, then I believe you. But if you, if I say, well, if we have some hematite and you pack some oxygen there, in air, but that then it's not valid, because you cannot put that much oxygen in there. So you need to keep it solid. If it became FeO2O3 plus water, then the water will go away. Then just dry FeO2O3. So that won't work. So you have to have the goethite go all the way down. So those are plotted as different geotherm, and the downgoing slab are the BCD and its colder part. So in that, it's perfectly all right. You keep it solid and you keep all the water and go all the way down. So if you think of is this a valid assemblage? Yes. I mean, the bulk iron ore, that's it's probably the most popular iron ore, starting from Iron Age. It had millions of tons of this material, but it's concentrated somewhere. So, but at some point, it's possible to bring this down to the, if it happens to be in downgoing slab, you can take this and put it down there. Okay, so we run an experiment of starting with this goethite, and at high temperature you decompose in this. So this is the valid phase diagram, and at the ambient temperature is the solid form. So we want to see at some point it may go to this, whether it happen or not. So again, Qin Yang run this experiment at low pressure is goethite, and the goethite stays up there, and then when you go to like 80 some GPa and later heat it, and then this phase come out, this pyrite structure come out. The sample, we put goethite inside the neon pressure medium to avoid reaction with the other. Then the neon peak is still there, but most of this, the pyrite phase, and except some of the star are the left, the epsilon FeOOH left unreacted here. Okay, so now we compare this goethite in neon versus the first experiment, the hematite plus oxygen. That one we made this FeO2, and this one you can see that all the patterns still agree. You also have FeO2. And later we got rid of most of the epsilon phase, so it's actually even purer FeO2. Okay, now we also have to prove there's a hydrogen there. So the hydrogen at this temperature, 1800 degrees, it's very mobile. So it diffuses out into the neon, and it shows as a hydrogen peak in neon. And it's at 50 hydrogen Vibron at 5130 something. And this hydrogen neon had been studied previously by Rubert, 1991, and they only studied it to 40 GPa, and ours said 80 GPa, so it falls right on their extrapolation. So this, there's no doubt, is hydrogen, and later we reduce the pressure, it actually just tracks back. So now we demonstrate this reaction is real. You at high pressure, the water plus plus the hematite will become FeO2 plus hydrogen. So the phase diagram will be like this: alpha, epsilon, FeOOH, and in fact, Chen Yang had one more experiment with multi-anvil in this region and more high diamond cell experiment in this region. And the geotherm is the slab geotherm goes somewhere on here. So it will become FeO. In the upper mantle, the top part of the lower mantle is still, it will be FeOOH, but once you go to deep lower mantle, this will separate into this and release hydrogen. So now the model is like this. If you have some of the goethite, it goes down and it will remain as goethite, maybe to epsilon phase. But once you reach 1800 kilometer in the middle of the lower mantle, it will start to release hydrogen and then leave out some of the FeO2. And FeO2 is stable. It's heavier than the rest of the the silicate, so it will keep dropping down, and probably accumulate at a core mantle boundary, and probably scatter somewhere. And then if you say, well, would that react? If the lower mantle is very reducing, would that react back to this? I would say no, because this has to depend on the solid reaction, solid diffusion. If there's no other. Solid diffusion is extremely slow. I mean, if you're a kilometer away, you have extremely different oxygen viscosity. There's no problem. You can keep that. So it's just like what is oxygen viscosity on surface? We'll say, okay, oxygen, free oxygen plus hematite. But also, just a few meter down, they also report of a very reducing. There's native iron, and in some rock, and the native iron plus hematite. So on the surface, you can say, well, the temperature is low, and so the reaction, the diffusion rate is not that fast. But even in the lower mantle, in all diffusion experiments, if you have a kilometer away, nothing's going to balance. So, so the thinking is, before it was just difficult to take something so oxidizing down there. But now I think that you can have very reducing patches of like O2 just sitting there. Even so geological time, it's not enough to react and get rid of it. But occasionally, if this thing happened to be carried up by some plume or some mental dynamics, then it can come up, the oxygen will come up as in the air. The hydrogen, on the other hand, is very mobile. So once the hydrogen became free, it can go to diffuse its way out, or it can react with carbon, with other things, and so come up with many different ways. So so basically, hydrogen cycle and oxygen cycle, they go together down to these steps, and then they separate their own way. Okay, this is if you say, well, all our evidence from the diamond inclusion shows it's very reducing or something, but actually it's not. If you just like Kathleen McCammon in 2005, he published this paper called Paradox of Mantle Redox. What puzzles her is often you see a lot of FP3 plus in diamond inclusion. Why? Okay, so if this is all still using the same idea of the oxygen viscosity using the QFM, buffer system, and what we still thinking all those based on the surface experience of the buffer system. So a lot of things, this is from her figure, that she was quite puzzled by why this the Fe2 plus 3 plus ratio is not correct down there. But the sample we have from the depths, we don't have any sample from deep lower mantle. We have some sample from upper mantle, and usually it's assimilated on the way up. The only thing you can be sure that not assimilated from diamond inclusion, but diamond inclusion itself is very selective. It has to be carbon, free carbon chemistry. So if there is not uniform, if it's a very uneven distribution, you only select the one which is coexisting with free carbon. So I don't think any of this is really valid to say that it's uniform that way. Okay, so now let's go look back to the conventional wisdom number 1. The mantle is uniformly reducing. The conventional wisdom is the lower mantle is iron Wuster buffer, and the upper mantle is somewhere between these two. That's not so sure, but certainly if I say it's here, it will be it will be like crazy. And then there's also one related to this is that when we say that the maximum, when you have higher oxygen viscosity, then the higher Fe3 plus ratio, which also sounds very intuitive, and of course that's because you think in terms of the stoichiometry, you think more iron 3 plus there, then it's more oxidizing. Okay, that sounds very natural. So actually, both of these two are invalid. Okay, so first, lower mantle oxidation state can be very uneven. So I'm not going to say that lower mantle does not have iron Wuster buffer. I mean, probably a large part of that, but I would say that there could be many patches of like hematite and this pyrite space buffer. So it can be very uneven. It can be anywhere there, but you just don't see those samples. Okay. Another one is that to say that the maximum action viscosity in iron or 3 plus, like a hematite before the maximum hematite. But this is completely counterintuitive. Actually, the maximum one oxidation state is Fe2 plus. So you're reducing the hematite, you're oxidizing the hematite, but the Fe3 plus becomes 2 plus. Okay, so that's sounds also counterintuitive chemistry, but what's happening here is the iron is reduced from 3 plus to 2 plus, but the oxygen is oxidized. Before oxygen is all 2 minus, but now some oxygen is 0. You have OO bond here. Okay. So this we also just after this work we have done some spectroscopy, iron spectroscopy, look at whether this is indeed Fe2 plus. We look at emission spectroscopy and found this is indeed Fe2 plus. Okay, the second conventional wisdom is hydrogen is very reducing. That means that hydrogen and the water, if the hydrogen and oxide meet, then they will take oxygen out of the oxide and form water. That's the reducing the way that hydrogen as a reducing agent. But at high enough pressure, actually hydrogen in deep lower mantle is oxidizing. It can give out oxygen to oxidize even hematite to become FeO2. So it's very counterintuitive in here. So what we're saying is that the dashed line are the conventional wisdom phase diagram that water can coexist with iron, and water can coexist with FeO and so on. Those are the timelines. But at high pressure, once we establish this timeline, then it truncated everything else. That means none of this will exist. So it will be the new phase diagram, ternary phase diagram will be the solid line. So the FeO2 coexist with hydrogen, and the hematite can coexist with hydrogen. So all those can coexist with hydrogen, will not form FeO2. Okay. So the impact on the other different branches of earth science. First, let's say the mineral physics, and recently, I mean, it's 10 years ago that was discovered there's a phase called post-perovskite at the pressure near core mantle boundary, and so it took 10 years to sort out everything about post-perovskite, and so finally, K. Hirose, his group initially discovered the post-perovskite, published this paper, The Last Word or the Last Mantle Transition Post-perovskite. So that book was published by HGO. But the post-perovskite may not say the last word, because now the core mantle boundary could well be something like pyrite structure. Okay, perovskite itself is a big group. It can accommodate a lot of things, but pyrite is even more accommodating. Pyrite can accommodate Fe, this demonstrate, but also can accommodate Mg, and it's this pyrite structure Pa -3 MgO is known at ambient condition, but Sergei and Alice also work on high pressure form. Then they found several other forms. Okay, so this FeO2 pyrite structure, it may form solid solution with MgO2. Also, SiO2 at high pressure is also pyrite structure. It may also form this. And this structure, as I said, is very accommodating. It can take many different transition element, real earth element. It may have the impact on the trace element geochemistry, because it's much more accommodating than many other crystal structure. Of course, there's a large amount of work has to be done, and we have tried some magnesium wolfstite reactor with oxygen to see whether we can make FeMgO2. And that experiment was not so successful because, well, it is successful in another way. It formed something, but that phase is not the pyrite structure. It's more complicated structure. It's a lower symmetry. So you can say that this will probably open a large, a new area of many possible phases here. Okay, pyrite structure is not only it can take the cation there, it also is good to take many different anions. For instance, the original pyrite itself, plus if you just go across the periodic table, this is also known in pyrite structure, and all those you can have a molecule like an S2 Cl2. You can all put in this comfortably. They may also form solid solution with this, and so those are the like 2 weeks ago, like Hirschman gave a talk about all those halides and sulfur and all that all the volatiles. A lot of volatiles can be put in this. So it's a very interesting, I mean, simple, very interesting structure. Okay, now, what's the impact in geophysics? Immediately you can think of it, say if you have FeO, you have O2 patches in a deposit on the core mantle boundary, this will have a very low velocity because the iron is heavy. And indeed, we have done some nuclear resonance in scattering, and the shear velocity is as low as 5 kilometers per second. It matches very well with the ultra low velocity zone, which is about 10 to 20% lower than the average of the shear velocity over there. This has been a mystery of for the d double prime layer. Okay, even for the biochemistry, and one of the big puzzles in Earth, for Earth's atmosphere and ocean is why we have oxygen in the air. I mean, the first half of the Earth's life, before 2.45 billion years, giga years ago, there's no oxygen in the air. You measure in trace amount of less than %. Then there's a big event called Great Oxidation Event, happens around that time, and then oxygen suddenly rises to present level and it sort of fluctuating around there. So this obviously is important to our existence. I mean, we are aerobic animals, so we have to have oxygen here. But where does oxygen come from? And all the explanations so far, because you think that the mantle is very depleting oxygen or is very reducing, so you cannot get it from there. So oxygen all comes from some biological reaction. So this topic, the Great Oxidation Event, actually is the current biology topic, and like this paper published that say but still puzzle even biologists. The theories are like oxygen come from some the oxygenic photosynthesis of the cyanobacteria. Bacteria. This kind of bacteria exists before the oxidation event, and but oxygen is a poison to them, so it will kill them. And so presumably they form the oxide, then they die. And so now it's oxygen atmosphere. But if we have patches of a very rich in oxygen like FeO2, and we know we release pressure to like the upper mantle, it will decompose, it will give out all the oxygen. And so you can imagine there's certain geodynamic cycle, and suddenly all this come up. You say, well, what particular event will that happen? I don't know, but it could be accidental. Just at some point that just accumulating enough will come out, or it can be there's some instability that if you have too much there, it will come up as a whole. Why 2.5 billion years ago, that I don't know, but I think that would be a very good topic for geodynamicists. So I'm not saying that we don't owe our life to this cyanobacteria. I'm just saying that this could be another explanation. Yes?
Dave, the oldest stromatolites, there's still some question about that, but they could be anoxygenic, non-oxygen photosynthetic bacteria.
Yeah.
And the biomarker evidence of cyanobacteria 2.7 has just been completely refuted.
Mm-hmm.
It was contamination in the drill course because they drilled with oil on the drill stem.
Yeah. I agree. As I said, I agree with that. The bacteria probably is very. I mean, we probably owe our life to the bacteria. But what I'm saying is the oxygen is not constant on surface. It could be also be a large amount of oxygen come out there.
Yeah, and this shows that cyanobacteria may not have been the relevant organism to release oxygen into the atmosphere. So the biogenic hypothesis is being questioned.
The biogenic is, say, if you release oxygen, it could be in form of CO2 or CO or some other toxic oxygen, right? But the biology is also, so I'm saying that there could be about abiotic origin of oxygen at 2.5 years.
Completely agree.
Yeah, okay. So this is not, here I'm talking about total oxygen, not how oxygen converts from one form to other form.
I understand.
Okay. Okay, so thank you.
Okay, questions?
Yes.
Well, that's a very interesting, definitely interesting finding. We have a great impact. But my question is really, if you FeO2 and stable, whether it's reactive for the, I mean, right now you're presenting this as a separate phase. So the question is whether this is, can be reactive as a perovskite, for example, and that would be certainly interesting.
That's a very good suggestion. So right now I'm only consider Earth as 3 elements. Obviously Earth has more than 3 elements.
Tim, and
so you sort of mentioned this in your talk, but I'll just say it explicitly. So the compound you form is a peroxide, FeO2. So in an ideal world, the way to think about this is you have an oxygen molecule, and you put 2 extra electrons in the pi G star orbital. It becomes isoelectronic with molecular chlorine, for example, or for nitride, which have 4 extra electrons. All these compounds form a pyrite structure, so like platinum nitride, for example, and all the known peroxides that are common with alkaline metals and alkaline earth metals like barium and showed magnesium peroxide. So then in that case, it's not surprising that you see Fe2+, and I would guess it's an insulator, and you show the bond length, and it probably has an interesting Raman frequency that corresponds to OO single bond. So I just am trying to understand this argument about oxidation state. Just because you have more oxygen, that's not defining the oxidation state of the iron. So in this case, you have Fe2+. So I mean, walk me through this argument that this is like a more oxidized, when actually the iron is more reduced than in some of these other iron oxides.
Okay, I'm saying more oxidized means higher oxygen gas-state. But then, and actually, the question is good. So I'm saying that the phase FeO2, you can talk about FeO2 is more oxidized than Fe2O3. But you cannot say that Fe is more oxidized or reduced because of this.
You have to look at the electrons.
Yeah. So this is just a way of to understand that, but not to argue any of this, the terms. So the oxidation state. Okay, now another one is what you say is correct. That at ambient condition, because the charge defines everything. So the way to make peroxide is you have to really stuck the O2 as a molecule in there. The pyrite is the same thing. Okay, you have S2. But at high pressure, SiO2 became peroxide. If you really calculate ionic distribution, the silica, if you look at the charge near silicon, it probably reduced. I haven't done that. Okay, let's say this has an identical structure. Then you would say probably have a similar problem there. So the main message is at high pressure, each individual one, you have to look at the distribution is never completely zero, oxygen zero or Fe2+ or 3+. It's always some 2.1 or 0 point something there. So what I'm saying is it doesn't make too much meaning to discuss that. But just to answer the question that people say, well, how come it's oxidized? The whole thing is oxidized, but iron became reduced. In that sense. Okay.
So you had a question, and then I'll go to you.
Yeah, you mentioned about the band ion formation and that into the going through the subtraction, but in terms of the total volume, how much you would accommodate while we observe the lower band?
I didn't quite get you say band ion formation. Like people talk about band ion formation in the core metal boundary, right?
Yeah.
Are you talking about that paper?
Oh yeah, I just wonder the volume percentage, how much stuff you can put it in from the band ion formation in back then.
Okay, and if it's possible down there, you have similar composition as the band ion formation that you talk about a Nature paper by that paper, for most people, I think it's a tongue-in-cheek, so not too many people believe that. But they just saying that, okay, now you have a core boundary, you have iron oxide, which matches the ultra-low velocity zone, and on surface there are a lot of band ion formation, so somehow you get down there. So basically, that's what that paper said. Okay, so we did mention that in our paper, but the reviewer said take it out because that one no one believe, and you have much better story. Why talk about that? Okay, so what I'm saying is that iron oxide in the core-metal boundary, that is fine, but the way the band iron formation go down there has a lot of problem. Okay.
Dan and then Kyle. Yeah.
So it seems like the reason we have trouble thinking about about the chemistry that's going on here is that we all learned this electrochemical series sitting up here on the Earth's surface. You know that when you increase oxygen, you gas it, you oxidize metallic iron to Fe2+ and then to Fe3+ and so forth. And it really seems like what you're showing here is that the electrochemical series that we all learned is not valid at mantle pressures. I mean, we may need new experiments to. Do you see what I'm saying? I mean, if you look at the standard reduction potentials, you know, at higher pressures, those half reactions may be changing substantially and just moving right past each other, such that you know, our thinking about what's the oxygen fugacity might not even matter. The question might be what's the hydrogen fugacity, or what's the ferric iron fugacity, or something along those lines.
This is okay. When I give a talk, I try to make it simplified so it sounds like that's Tim's complaint. Okay, and it is. I think the complaint is valid. The other way of thinking is just instead of saying it's not bad, you have to think every of those conventional wisdom carefully to what it really means. Okay, and some of this, I think in general you can change it and make it better again, but you have to consider many things.
Right. I mean, do you think that we need new experiments throwing magnesium and silicon in there and looking at what the standard reduction potentials, you know, what those relationships actually are at high pressure to make sense of the, you know, some of the phase diagrams that you're getting?
Yeah, that's what the theoretical chemists or theoretical physicists are trying to do. I think that will make it better again. But just to call it simply, one say using the buffer system on the surface, it works very well. But if you keep using that, eventually at some point it will break down.
Colin?
I wanted to pick up on a couple of questions here. So I guess your model requires two things. One, you make goethite at the surface, and secondly, that the goethite can be subducted all the way down to the core mantle boundary, or at least to 1,800 kilometers. First of all, do you make goethite under early Earth conditions at the surface? And secondly, are you sure that goethite doesn't react during subduction with other minerals and never makes it down to 1,800 kilometers?
Yeah. So the first, if you just have goethite, so because this is everything is like we're trying to rebuild the whole chemistry again. First, we just start with the goethite alone. So we have to answer the question: the goethite, can you bring the goethite all the way down without breakdown? If it breaks down, then it cannot carry the water, right? So that one, so we did phase diagram, phase study. We did bring it all the way down.
Sorry, but how did you do that if you've got silicates?
Then the second question is if you put a silicate next to it, what will happen? Okay. Then you just like adding more component to it. And so far, goethite on the surface, at least the silicate is not a problem. Does not cause goethite to break down. So you can say, okay, now you put some olivine to it, maybe, and then spinel or the pyroxene or many other things that might happen. So of course we need to do that. But the first thing first is because all the discussion about oxygen fugacity start with mainly from iron oxide, right? So at least we established from that simple system, again, that you don't have to teach that you start with a simple system and see it go. But in this case, it looks like you put a silica there or Mg there. That's why the next one. That's why I said this structure is really accommodating. You can take many other.
Yeah, I mean, the most appropriate thing would be able to salt to do your experiments on to see if you can do that. But you haven't answered my first question: is do you make goethite?
Do I make for goethite?
Can you make goethite under the reducing conditions of the early Earth surface?
On the surface, yes.
It's stable.
Yeah, goethite is stable, and there's a big. Actually, it's and if you just put a piece of iron in water, next day you get goethite.
Yeah, but that's under an oxidizing condition.
No, but I can tell you that we've done reactions with like 500 bars hydrogen pressure, and we make goethite. Yeah, it's amazing. The thermodynamics is so favorable. It's right. You had a question, and then.
Okay. So we argued that you use the goethite, recycle the goethite to produce the FeO2, right?
Yeah.
That people argue. So I'm thinking maybe we can use the recycled hematite react with the water-rich mineral in the manufacturing zone. So that's maybe more reasonable.
That's right. So the question is, okay, now goethite, even though there's a iron ore, but iron ore is still very local. You don't have good iron ore everywhere, right? But if you put, say, so we did another experiment. If you just put any iron oxide with water even with pure iron, it forms FeO2. So it's actually, this you can get from the phase diagram itself. That's why this phase diagram I didn't get. Okay, this phase diagram means that if you put iron and water, go to that pressure, it forms this. This if you put this on this joint, it forms this. So we did this experiment, iron and water, and we're in the middle of doing FeO and water. So all those, but once you establish this relation, then just from phase rule, you don't really have to do an experiment. But you said convince people. But except that here, you also have FeH. That's another phase.
I mean, how about the recycled hematite reaction with the rubidite? What kind? I mean, the rubidite is water rich, right? Rubidite and
Greenwoodite.
Yeah.
Okay. Okay. So the question is, so the requirement is, if you have any iron, put in water, then you form this. So you have to have water, and rubidite can carry some water, a small amount of water, and there's several hydrospace there. So one thing is you're sure that there's some water down there. The water may be, so first you have to carry water down. Then water has to release. Once you release the water, this reaction will form. So that's all the sort of pressure temperature range. Right? So obviously there are more phase study need to be done. This is just the first show that the so again the focus here is to show that it's a low mantle. It's the hydrogen is actually quite oxidized. Water is, I should say, water not hydrogen. Okay, can release hydrogen if you establish this highline. Okay, so that's one key issue. Okay, then so it can be formed many different ways. You can get water from silicate. You can get from aluminum oxide, hydroxide. There's some popular new H phase and so on. But many ways, as long as you have water, you have iron oxide. Can be hematite, can be magnetite or wustite. They will form this way.
Sorry.
First of all, I completely agree with Tim that RNO2 in the pyrite structure is completely not surprising. So, but my question is, what will you cook in a diamond angle cell at say 100 GPa if you take a small piece of iron and then surround it with unlimited amount of oxygen and laser heat it? What will be the stable phase?
The iron and oxygen?
Yes.
Okay. Iron and oxygen form FeOH.
Oxygen.
Oxygen. Yeah. This is actually the first experiment we did. Fe and OH. It formed the complete zonation of this because the reaction hasn't penetrated through.
So, but have you observed then the pyrite structure?
For this one, it didn't go that far. Okay. So the first experiment we did was iron and oxygen. Okay, it formed a bunch of all of those intermediate things. And so many patterns, so many diffractions we couldn't resolve. So then we start with this. But once you establish this one, okay, now once we see this, it's not surprising. I agree with you. that peroxide is not surprising, just like MgO2. There's actually it's already known to have peroxide. But what's surprising is that this side actually no one has ever studied. The more iron oxygen rich than Fe2O3. Okay.
I actually found it. It's in the Landau-Bernstein.
Yeah. You have calculated and found it also, right?
Yeah, I presented it at E3 in 2012. But,
Yeah.
But also.
Probably no one believes that.
In the Landau-Bernstein is a known material in a 1980 paper. So I don't know what structure it is.
Yeah, I believe that the theoretician has calculated.
No, this is experiment.
Experiment.
Published in 1982. But what can I say? It's in Landau-Bernstein. So FeO2 is a gas-phase molecule that they crystallized it, but I assume it's.
No, I'm not saying that the gas phase. I say this.
No, I assume this was a crystal structure. They give the density and all that. But I don't know, any detail.
Zach?
Do the densities make sense, like that this would be a pressure-driven, I guess, decomposition of FeOH? Is FeO2 becoming very dense with pressure? I mean, because you actually measure densities of some of these phases. So do the thermodynamics make sense that it's pressure-driven?
The thermodynamics makes sense, yes. So you compare the reaction, the thermodynamics makes sense, yes.
Is FeO2 at like 30 GPa? Is FeO2
FeO2 will be
less dense?
So we did a reversal reaction. And also, the reversal reaction has to be done at high temperature. And then to low temperature, ambient temperature, we did reverse. So by just decompressing, it just decompose. It just somehow collapsed. We don't know whether it became amorphous or decomposed.
My impression is that whole evidence of the iron peroxide is based on X-ray diffraction, right?
Peroxide is based on X-ray diffraction, yeah. So single crystal diffraction.
Right. You showed also that the phase is transparent. It has some bluish color to it, right? So that said, I would really expect that iron O2 would be you would say good signature of it in Raman. Yes. Right.
Well, the Raman of FeO2 is difficult to get because it's not very transparent. Okay, but we do see hydrogen with Raman.
No, but you showed that the phase is transparent, right? You said it's translucent.
Translucent, yeah.
Right.
Yeah.
Meaning that you can.
It's possible to. If we work harder, you probably can see O2 vibration, right? But okay, so the next question is. Is it important to prove that O2 is molecule? Okay, what you're saying. And that's kind of secondary to, because we mainly want to prove this as a phase rather than to say, I did mention that this is a Fe2 plus or oxygen is 0, but none of this is exactly valid because the theoretical calculation also you can look at the ionic charge of the O is not exactly 0, and the iron is not exactly 2. It's 2 plus something.
So I have another question related to what you're trying to use to explain the great oxidation events. So partly this is you need the least oxygen. One of the things that would be interesting to look at FeO2, how it decomposes at high temperature. So right now you study the forward reaction to forming the FeO2. So the question is, once you're forming FeO2 and around the geosome, how is it going to decompose? Because you have Fe is a 2 plus and the oxygen. So the question is whether you're going to decompose the FeO plus oxygen or hematite plus oxygen. So those are all going to have implications of how they're going to react with the silicate on this clone-like events.
Right. This certainly is it will be a big project. I'm just talking about overall oxygen budget. If whether it's this FeO2 certainly has a lot more oxygen than than the surrounding mineral. So if this you have a large patch of this coming up, then the total oxygen budget will be increasing. And whether you do need that or not to explain the great oxidation event, and I think you still need bacteria to work. But whether the total oxygen budget increase, that's one question.
Yeah, I mean, if you want to make this convincing stories, then you need to do the mass balance, right?
Yeah.
So how much, after you
Total
go by
oxygen.
type of material you need to bring down to
Yeah.
bring it up to the
Right.
oxygen level increase
Right.
in the atmosphere. So that's a back of envelope calculation, basically. You should be able to estimate.
Right.
It's a reasonable explanation.
Right. The oxygen, because it's everywhere, so that means the background amount is very high. So you talk about the delta. Without this extra oxygen, you can probably make enough just by converting some of existing CO, CO2, but this also could bring in a large amount and enough to change the balance. That's what I'm saying.
So you've got 2 more. You're leaving later this week. So if you have any more questions, you got to ask them quickly. Because Dave will be gone for 2 months. Right?
Yeah.
Thank you very much.
Hey, that was perfect timing. Our seminar is just finished. Literally, we were just applauding the speaker.
So this is all part of how much extra oxygen you bring down. But that would be a good experiment for Wu to do, and basically look at the acidic if you want to really kind of advance in this low mantle environment.
Doesn't work, but there could be some other ratio. This could be complicated. Because MgO has a such FeO at different pressure. Another one, the SL2, eventually has the such also. Right.
Yeah.
So once you get SL2, then this argument of whether it's O2 molecule become not important. Personally, we also have the O2 molecule-like thing, but it's not a.
Yeah, no, but even the first question is stability field. Also, once you make the FeO2, and look at the phase diagrams, and what is the back transformations, which will be kind of the first order defines what region will be stable, right? And so if you decompose the FeO plus oxygen at a certain pressures and temperatures, right now you did the room temperature decompression.
But
Right?
we did high temperature. It decomposes into O2 plus Fe.